Hi, this is Karen. In this part of the tutorial we will discuss lossless compression. While important in its own right, it will also be a crucial building block when discussing lossy compression later in the tutorial. We'll cover lossless compression by going over some information theoretic basics first, while we will quickly progress to the main part of the session, the interplay between entropy coding and generative models. If you want to skip sections, again timestamps for this part are on this slide. Not surprisingly, the most important unit of information theory is information itself. We can think of information as a quantity that measures a reduction of uncertainty that an observation provides. The standard unit in which we measure information is the bit. More precisely, 1 bit of information corresponds to an observation that appears with probability half. Thus, information relates to a probability measure via its logarithm. A second key term besides information content of an observation is the cross-entropy. Cross-entropy measures the expected information of a discrete random variable under a distribution Q. The cross-entropy is an upper bound to the entropy, the expected information of the random variable defining the probability space itself. The discrepancy between the two variables is the Kullback-Leibler divergence of these respective distributions. So you may wonder how these terms are related to compression exactly. To see this, let's investigate the lossless compression setup. The goal of lossless compression is to find a binary representation M of a discrete random variable X, such that the size of the representation is as small as possible, while X can be reconstructed perfectly. From Shannon's studies, we know that the shortest length is lower bounded by the cross-entropy of the true data distribution of X and a model of the true distribution. Functions that map from X to M will be referred to as encoder. Inverse mappings will be referred to as decoders. The tuple of an encoder and a decoder will be referred to as codec. An optimal codec is a codec that can achieve the cross-entropy bound. Such codecs are also referred to as entropy coders. We will represent them in the tutorial as follows. The gray box represents the bit stream, M. Within, we will denote the change of the length of M, while encoding a symbol. And equivalently, we will use decoding, but indicating the reduction of M by the dotted line. Next, we will investigate optimal coders. At the end of the session, I want you to understand entropy coding as a basic operation that turns a symbol into its representative shortest binary code given a density model of the data. First, I want us to build a naive codec. So consider a random variable X with the event space A, B, C, and D. We can assign a 2-bit code to each event, defining our codec. This codec is also referred to as fixed length code. Note how we do not rely on a data model here. Encoding a message of 8 symbols in this example hence leads to a coding cost of 16 bits. Fixed length codes are parallelizable and allow for fast I/O operations, thus are often preferred in practice. However, generally, we cannot reach the Shannon bound. For example, when we have a large event space, of which many events are very unlikely. So we can do better than this. Let us take the same random variable, but allow for a variable length code, and extend the table by the density model P, the information content H, and the length of the proposed code. Our idea here is that likely events should get shorter codes, while less likely ones should get longer ones. When we now compute the length of the same message as before with our new codes, we see that it is shorter by 2 bits. So how can we construct such codes and also make sure that they are still uniquely decodable? While the tutorial does not allow to go into details, we construct codes by constructing corresponding binary trees. Each leaf corresponds to either a 0 or 1. Now likelier events are assigned higher up in the tree, thus cause shorter codes, whereas less likely events are assigned lower down in the tree. The precise rules for construction of these trees is beyond the scope of the tutorials, but definitely worth investigating. Note that the set of rules is not unique though. One well-known set of rules is known as Huffman codes, whereas another set is known as Shannon-Fano codes. However, note that in contrast to fixed-length codes, we have given up fast memory access to any particular symbol. In fact, for all variable length codes, we will not be able to tell which bits in the bit stream M belong to which symbol before decoding. So we will go into details about this point later again. So don't worry if you didn't get that just now. And further, assigning binary representations to each event separately means that we assign at least 1 bit per event. And this can be a problem for low entropy random variables. So for example, consider a Bernoulli with success likelihood 0.99. With our method, we still assign 1 bit per each event, even though the optimal code length would be just about 0.08 bits per event. So a solution to this problem is considering multiple events jointly. Recall that Stephan has introduced the concept of arithmetic coders earlier in the tutorial. I want to extend his thoughts and talk about how these codes are built. First, consider floating point numbers from 0 to 1. Now consider all possibilities for 2 consecutive events with the event space A and B. The size of each event corresponds to that joint likelihood. And finally, check out floating point numbers, but represented as binary numbers at different levels of precision. On the right, 1-bit precision, and on the left, 4-bit precision. If we want to construct a code for an event, say BA, we need to look for the corresponding code that is fully covered by the event, while being as short as possible. In this case, the code would be 110. Seeing this construction, we can imagine that instead of using floating point numbers, we could use integers from 0 to a large number. And this idea has given rise to so-called asymmetric numeral systems. Without going into details as to why, know that the floating point-based constructions of arithmetic coders gives rise to a queue-like data structure after encoding. This is a first in, first out data structure, while integer-based constructions, such as A and S, gives rise to a stack-like data structure. Here, after encoding, we find first in, last out data structure. Different structures are important in different scenarios. Now, we will be moving to the main stage of the tutorial, the interplay between entropy coding and generative models. So let's review the game plan. In the previous sections, we have talked about entropy coders, aka operators, that can turn any discrete symbol and its respective density model into the shortest possible binary representation M. We have not talked yet about how we can possibly learn such a discrete density model. But as machine learners, we know that generative models are the place to be for this task. So next, I want to go through the choices of generative models that we have. Note that our goal is to identify learnable invertible functions that model conditionally independent image pixels via one-dimensional Bayes distributions to be used in entropy coders. In this slide, I have classified commonly used generative models into their ability to compute likelihood models for any given event. Explicit models can do it, implicit models, such as GANs, cannot do it, hence implicit models are not interesting for lossless compression. We will thus investigate the explicit category only. Within this category, we find a split between tractable and approximately tractable models. At first glance, tractable models seem to be the only viable type of generative model suited for our course, thus we will investigate them first. However, at the end of the tutorial, we will also look into approximately tractable models, as we may apply them with some trickery. So let's start with autoregressive models. Autoregressive models are defined by the following likelihood model. Here we model pixels recursively, or in other words, we start by modeling a specific pixel. The likelihood model of the next pixel relies on the previous one, and any following pixel relies on the previously seen ones. The illustration here shows that on an example. We aim at predicting the red pixels, likelihood that is seen on top. The density is conditioned on the blue pixels. In particular, this is often achieved with masked convolutions. There are many such autoregressive models. I put a few notable ones on the slide. Also note that autoregressive components are part of almost all other types of models that we will be discussing today. It is fairly straightforward to compress images with such a model. For each pixel of each channel of an image, we get a one-dimensional density that we can use in an entropy coder. So consider this message here with 4 pixels, x1 to x4. we will start with a prior on x1. This density is given to an entropy coder, and it will increase the length of the binary representation m by negative log p of x1 bits. We continue with pixel 2. The density here lies on pixel 1 only, and we continue with this scheme for pixel 2 and 3. When using an arithmetic coder, we need to code pixel 1 first and pixel 4 last, as when we decode the first encoded is the first decoded. However, for an ANS version of this model, it is also possible, but we would need to code pixels in reverse order. So I show this here. A pixel CNN is a generative model that uses autoregressive components to model images pixel by pixel, decomposing the joint image distribution as a product of conditionals. Pixel CNNs are much faster to train than pixel RNNs because convolutions are inherently easier to parallelize given the vast number of pixels present in large images. And this can be an important advantage. Before we move on to the next type of generative models for lossless compression, I want to go over some concrete architectural details of Pixel CNN++, one of the most commonly used autoregressive models to date. So the conditioning for any pixel is based on previous pixels of all color channels. When pictures are large, we cannot condition on all possible pixels anymore. Hence, the authors propose downsampling the image in order to summarize regions of the image and then help conditioning in that way. The output distribution for each pixel is a mixture model with discretized logistic distribution components, allowing for quasi-continuous discrete pixel models. Later models use mixture models with different base distributions, or learn the discrete CDF directly, as evaluating the discretized PDF of a model is equivalent to 2 CDF evaluations. So far, we haven't really talked about how to determine the parameters of our mixture distributions, so the output distributions of this model. The authors proposed to so-called amortized inference, meaning one large neural network gets the inputs, aka the conditioning pixels, and spits out the mixture parameters. And the architecture looks as follows. Note that the authors include skip connections for better learning and further find dropout to help generalization. On one hand, the sequential nature of entropy coders and autoregressive models make them perfect companions. However, in practice, one pass through a pixel CNN takes much longer than an entropy coder call. Hence, we are looking for models that parallelize some of the computation, but remain tractable. A class of models that fulfills this requirement are normalizing flows. Normalizing flows are typically defined for continuous variables. We would start by a simple base distribution, such as a high-dimensional standard Gaussian, and we can then apply K-invertible transformation to achieve ever more complex distributions. After K-transformation, we hope that the density model matches the data distribution. We train this model by training the cross-entropy of data distribution and density model, which also happens to be our expected code length. As we cannot compute the objective directly, we use the change of variables formula to compute a computable version of the objective. Note that the Jacobian in this formulation is generally a very expensive term, and much of the normalizing flow literature evolves around finding families of transformations for which we can compute the Jacobian more easily. However, luckily for us, for discrete random variables, the Jacobian equals 1. So our main problem is not to find an easily computable Jacobian, but to find invertible mappings on discrete alphabets. So again, let us look at a specific implementation, here integer discrete flows. We want to learn distributions on integers between 0 and 255. This is a natural representation for RGB images. And as for the pixel CNN, we make the base distribution for the mixture of discrete logistics with some learnable parameters. Another key component of this proposal that closely resembles the discrete form of the real NVP architecture are factor outliers. Factor outliers allow for more efficient inference in hierarchical modeling, in that only for a part of the dimension we model the correlation while we let another part pass freely through the layer. So consider this example here. The discrete input x is sent through an invertible function, here purple, then split, and only part of the input will be again transformed by another invertible mapping, again here in purple, and later both representations will be unified. So let us investigate the purple functions. In integer normalizing flows, coupling layers let a part of the input pass while another part is linearly combined with the second part. Note that we have to round the second part to ensure discrete outcome, and further, H are densenet type architectures, and finally we use STE to guarantee gradient flow through the rounding operation. The last tractable model I want to discuss are probabilistic circuits. Probabilistic circuits are an umbrella term for graphical models that allow for tractable computation of likelihoods, marginalization over variables, and conditioning in linear time. While this type of model is the least flexible, it is also the most computationally efficient. We can build probabilistic circuits out of three components: input nodes, sum nodes, and product nodes. The idea of PCs is to combine mixture models of base distributions into a directed acyclic graph. Hence you will see the interplay of product and sum nodes as in the illustration on the right. As for all tractable models, the training objective again is the cross-entropy bound, and as opposed to other models that are mainly trained via SGD type optimization scheme, this model class is typically optimized by closed form solutions. So for example, by understanding the PC as an exponential family member and computing updates accordingly. Applied to image compression, so this could look as follows. Note that this architecture built local mixture models of image patches. Finally, I want to leave tractable models and discuss how we could use latent variable models as compressors. The class of latent variable models is highly flexible, and most operations required to compute with such models can be parallelized, making them an attractive choice for model-based coders. A latent variable model is specified in terms of a joint distribution Pxz between x and a latent variable z. We assume that the joint distribution of a latent variable models factorizes as P of z and P of x given z, and both of these are tractable. As for tractable models, we wish to optimize the cross-entropy bound. However, here, computing the marginal P of x is often intractable, hence the name. So to train these models, we typically use a surrogate objective that is an upper bound to the cross-entropy bound, the so-called negative evidence lower bound, or NELBO. The variational autoencoder is one of the most well-known variants of this family of models, as illustrated on the slide, but there's also hierarchical and sequential variants of latent variable models. The fact that P of x is not tractable means that we cannot directly encode x onto M. Hence, when building codecs, we need to make use of the distributions we do have access to, the joint and an approximation to the posterior distribution we call Q, the approximate posterior. The naive way of coding under these constraints is to use the joint to code samples from the empirical joint. To understand what I mean concretely, let us look at the two-part codec that uses an underlying arithmetic coder. The message we aim to encode is x1 and x2. First, we sampled z1 from the posterior. This action does not influence the bit stream, hence there is zero change in the bit stream. Next, we encode z1 with the prior P of z, followed by the image x encoded with P of x given z1. Note that we could have also used an ANS coder, but note that in that case we would have to switch the order in which we encode z and x so that we can decode correctly. Remember, Q versus stack data structure. In either case, when we collect the orange and red terms, we can compute the average code length. This comes out to be the cross-entropy of the empirical joint and model joint. This is larger than the elbow bound and larger than the cross-entropy of the true data distribution and the intractable marginal. Before we discuss how to improve this bound, let us check out one example that uses this codec. The L3C model is a hierarchical latent variable model of discrete latent variables that are trained via soft loss. The idea behind the architecture is that we successively refine our image prediction, only having to code the residuals. Next, we want to refine our idea and improve the overall code length. We will use the joint for coding, but instead of generating samples from Q via a generic random number generator, we will use bits from the bit stream to decode Q, which will give us samples just the same. I want us to use the ANS 2-port coder as a reference, and then compare this to our idea. See how the only thing we need to change is to replace the sampling strategy for Z with a decoding operation. So now instead of adding 0 bits to the code length, the sampling step removes bits from the bit stream, hence the name bits back coding. So again, old version, the purple operation does nothing to the bit stream. New version, the purple operation removes bits from the bit stream. So now count the operations into the code length. This code length comes out to be the Nelbo bound, which is better than the previous bound, even though we cannot reach the cross-entropy bound. However, there are bits-back variants that implement multi-sample bounds that are tighter bounds on the cross-entropy bound. Further, there are variants that work for hierarchical and sequential latent variable models, and this type of codec can also improve compression of set structured data.